Thanks, Ethan. Like you said, I'm Chris Galbraith. I'm a data scientist at Google Cloud. I'm going to be talking about customizing threat intelligence with a metric learning approach. Great, there it is. Cool. So yeah, we're going to get started. I'll give like a high-level problem formulation. I'm going to talk about some general characteristics of threat intel data. Go through, why heterogeneous object embeddings are a natural solution to this problem. Go into detail in our modeling approach and cover some results. Okay, so the threat landscape is vast, right? We have hundreds of thousands of reports, thousands of malware families, hundreds of threat actors and targeted campaigns. And these things are shifting and evolving all the time. So as a threat analyst working at an organization, I might sit down and ask myself, where do I start? How can I proactively defend myself against the most relevant threats? So that's really our goal, right? We're going to try and take the semi-structured, unlabeled and large-scale cybersecurity data set and try and make it actionable for these practitioners, right? So they can quickly defend themselves against their most relevant threats to their organizations. And what do I mean by threat intelligence data? Well, threat intel data is a massively heterogeneous object ecosystem. Here's a picture from ImageGen. I asked that, what do you think massively heterogeneous threat intel data looks like with threat actors, malware families, and vulnerabilities, and it produced this nice picture, right? But we have basically a lot of different objects with different contexts, right? So threat actors, malware families, vulnerabilities, reports, lower level features like indicators of compromise, files, URLs, IP addresses, et cetera. And then, groupings of these objects, right? So targeted campaigns, corresponding to activity over time for like a particular threat actor targeting a given region or something like that. So very different granularities here, different scales. And typically, how we visualize this data or how practitioners use this data is they organize it into a knowledge graph. So, if we think back to like Kyla's talk yesterday about attribution, right? After the analysts do attribution for a particular threat actor targeting a location, they'll typically organize it in a graph, right? So here we have, threat actor nodes here in beige, like area APT groups, and they use a variety of different malware families, right? These pink nodes around them. And then they attack various different industries and locations. These are these orange and yellow here. And you can see it's a very dense graph, right? Like we see a lot of activity in the same areas with different threat actors, different contexts, different goals. So let's kind of take a step away from this detailed graph picture and like abstract to this cartoon graph, right? So essentially what we have is like a little sample from the graph, right? We have our actor nodes again in beige. There it is, right? Our threat actor nodes here in beige, right? They're related to various malware families in pink, different reports, campaigns, et cetera. Right? And not only do we have these highly heterogeneous items, but they also have heterogeneous features and feature distributions, right? So for example, if I pull up UNC1337, it's this fictional group, right? This is going to be represented as like a JSON object with different characteristics for threat actors. So things like, the industries and locations they target, the source location of the threat, the TTPs and vulnerabilities they tend to use, right? And then, we have different features for other objects. So for example, the malware family beacon, we see some of the same observations, right? Like industries, beacon has been used to target in the past, the TTPs and vulnerabilities it exploits. But then we have new features like, malware role capabilities and impacted OS, right? So is this a ransomware or botnet, right? Whatever this might be. Okay. So I hope I've sold you the idea of heterogeneity in threat intelligence data, right? Heterogeneous objects with different features, different feature distributions. So we're going to approach this with heterogeneous object embeddings. Yeah, so like I said, data with different modalities or feature distribution is increasingly common in practice. So the ML community has kind of adapted with multimodal systems and approaches. And in particular, there's this vast amount of literature on learning latent user and item representations for personalized recommendation. It's been applied in a variety of different contexts. Kind of like the seminal paper in this, I think, is this first one from social media, Pinner Sage, taking multimodal inputs like text and images and videos and using that to drive recommendations on someone's Pinterest board. But it's been applied in a variety of other areas like search, travel, and retail. So this is kind of where we drew the inspiration for our approach. And here's the basic idea. So we're going to take our heterogeneous threat intelligence objects, right? So here we have actors, malware families, campaigns, et cetera. We're going to pipe them through some machine learning model. And that ML model is going to give us, vector representations of these objects. So we're taking the JSON blob, sending it through some ML model, and coming out with some high dimensional representation of these objects we're calling embeddings, right? So here I just have a simple, 2D example. In practice, these are much larger. And then at inference time, when, our analyst comes and says, hey, what matters most to me? We're going to take, their interest notions, that analyst's interest notions, right? So things like, what industries and locations do these threats target? Do I worry about ransomware or threats from Iran or Russia? We'll pipe those through the same ML model and we'll embed them in this same embedding space, right? So at the end of the day, we'll have, interest notions embedded alongside, our threat intel entities. And this is going to enable like a variety of different tasks. So here I just have a very simple recommendation example, right? Again, we have our picture here with our various objects embedded in our space. Let's just say this is, hey, I care about threats targeting the USA government, right? We're just going to do nearest neighbor search in the embedding space to get our recommendations, right? So the first object I'd sample here is report 2 because it's closest in the space. And then, maybe we have a technique to generate, some reason or explanation to that user as to, why this is recommended. So, hey, this is discussing targeted activity in the government sector, and so on and so forth, right? So next we might recommend malware family 2 with some reason. Threat actor 1, etc. Okay, yeah, so like I said, a lot of different use cases for these heterogeneous embeddings. Information retrieval, like I showed on the last slide. There's one other interesting use case, calling it like fuzzy pivoting, right? So essentially like using the embedding space to say like, hey, what are the most relevant vulnerabilities given this threat actor embedding, right? Instead of having to go back to our knowledge graph and perform manual queries, we can just kind of let the model do it for us, right? We don't have to do all these hops through the graph. You can use these for a variety of different downstream tasks, object clustering, features into other downstream models. And one really kind of fun use case is in scoring, right? So imagine you have like a variety of different scoring sources, right? So confidence, like how sure are we that this threat is actually malicious? Severity, like what's the implication if we get hit by this threat? And then personalization, how is this relevant to us? So if we can kind of combine those 3 scores, we can get really solid customer-specific outcomes. All right, so I hope I've sold you on the benefits, right? We get efficient information retrieval. This approach is going to be really easy to extend to new objects over time. Enables a lot of different use cases, and really it's just going to enable a personalized end-to-end SecOps. But it doesn't come without challenges, right? So anytime you're dealing with highly heterogeneous data, there's some challenges in training machine learning models that we've encountered. Talk a bit more about that later. When we think about the recommendation task in particular, like this problem doesn't really conform to our traditional setup, right? We don't directly observe user item interactions like you would at Netflix, where I've seen your movie watching history. Also, unlike most recommendation setups, subject matter expertise is needed to assess results. So like we need to hand off these recommendations to threat intel analysts and get some verification that what we're doing is valid. And then maybe most importantly, the results of this are going to be highly dynamic and time sensitive, right? Threat landscape shifting all the time, so we need to be able to account for that in the model. Okay, so let's talk about the approach that we took. We tried a bunch of different stuff. From heterogeneous graph neural nets to knowledge graph models to binary classification, just trying to predict relationships in the graph. But what we found was that a metric learning approach was really solid and gave us a lot of control, and in particular, using triplet networks. Okay, so how do you train a triplet network? What does this look like? We have all our threat intelligence objects. They have their associated features. Here's like a sample of them, right? I targeted industries, locations, whether or not it's a distribution or ransomware group, et cetera, TTPs. The basic idea here is that these object features are going to get mapped to that vector embedding via a series of transformations, right? Deep neural network. And the transformations, we want to update them at training time so that more similar objects are closer together in the embedding space than more dissimilar objects. And in practice, this is like your typical triplet network. Hopefully you can see everything here. Essentially what we have is, we'll have 3 objects. This is our triplet, an anchor object, a positive object, right? So, and a negative object. They go through a network architecture here, right? They go through the shared network architecture to produce embeddings for each of them, right? So you can think this is actually really just one neural network. I've just repeated it 3 times in this slide. They're all going through the same network. But we'll get an embedding for each node, right? So an embedding for the positive, the anchor, and the negative. Then what we're going to do is we're going to compute a cosine distance between our pairwise comparisons here. So the distance between our anchor node and our positive node, and also between the anchor and the negative, and then pass that through a triplet loss function. In practice, triplet loss is pretty simple. Essentially what it does is it enforces that the anchor and the positive are closer together in the embedding space than the anchor and the negative, subject to some margin parameter epsilon here. So we have like an epsilon radius around the anchor, and you want the positive within that radius. Cool. Okay, so yeah, let's talk a little bit about the shared network architecture, right? So here I'm just zoomed in on this guy. We treat this as a set encoding problem. Here I've just selected 2 of the features, industry and location. Okay, that's, but basically what we do is, each of these features is going to be treated as a set of observations, right? So for example, for industries, like you might have financial services and insurance. Locations, you might have USA, Singapore, Malaysia, et cetera. And we're going to treat each of these features separately. So each of them is going to go through their own embedding layer, right? So we would embed financial services, right? Embed financial services. Okay. And embed insurance, get some d-dimensional embedding for each of those observations within that feature group, sum them up, and then do this across all features, right? So each of the features will get some d-dimensional representation. We concatenate across our different feature observations, send it through some sequence of hidden layers, and you get your object embedding as output. Okay. There's a variety of different ways we can kind of control the behavior of the model, right? Whether it be from feature selection or engineering to the model architecture. But what we found is like the most important thing in order to gain semantically meaningful representations of these objects is how we establish our batch sampling procedure to construct triplets. So I'm going to bring back our toy graph from earlier, and we're going to use it to sample. So the first step is sampling an anchor node here. We're going to grab APT3. Next, we're going to sample a positive from the graph structure, right? So some node that it's connected to here, we're going to grab the malware family Xenorat. We'll sample a negative from somewhere in the graph that it's not connected to. So in this case, we're going to grab the malware family UPS. We'll construct our triplet. Here I'm going to represent this as anchor, positive, negative. And we'll just repeat this until we've hit our batch size criteria, right? So our next iteration, we might come through and grab this report. And then our positive will be this threat actor UNC1337 it's connected to. Our negative will be FIN8 not connected. So that's the basic idea. And what we found was that this model is pretty good at learning the semantics of the threat intel graph. Right? Does a really good job. However, like when we actually sat down and talked to practitioners, we found that there's still a gap between what they'd want to see in recommended entities versus what the model was producing. And what we found was that we needed to infuse additional contextual information or knowledge that really wasn't readily available from first order graph connections. So what we did is we worked with our subject matter experts. So this is customer-facing threat intel analysts on a variety of different teams, really, and developed a pretty simple heuristic algorithm that we can use to rank actor and malware threats for a limited set of inputs. So this is not as flexible as the ML model, right? It's limited to only threat actors and malware families. It's not really extensible or scalable. It took a while to develop. This wasn't easy, but it's going to help provide some guidance during training to get the model to kind of behave how the analysts expect. Okay, so what does this look like? Right, so say we have this pseudo customer here. Let's say it's some Australian-based company concerned with financially motivated malware threat, right? We pass that through this algorithm, and it'll just spit out a list of ranked threat actors. So here, the top actors have been known to target Australian companies and ransomware, where the bottom ones are distribution clusters not known to target Australia or Australian companies. And we're going to do a batch sampling procedure fairly similar to what you saw on the previous slide. So, right, we'll sample a customer representation. So you imagine we have many of these customers here. We'll just grab this one, right? It's Australia. We'll We'll sample a positive from one of the top ranked threat objects. So here, fin11 is the second one. We'll use that as our positive. Sample a negative from one of the bottom ranked threat actors, and we'll form our triplet. And then we can just repeat this process up until we hit our batch sampling or our batch size criteria. Okay, let's talk about some results. So we have a variety of different metrics and ways to evaluate these models. I've just selected a small sample here. Recommendation entropy is very important, right? So this is essentially a measure of, as we vary inputs to the model, do we get different recommended entities, right? We favor models with higher entropy. If it's low entropy, you can imagine we're going to recommend the same objects to input. We look at freshness, right? So this is basically looking at the last confirmed activity for a given threat object. We prefer to recommend threats that were active more recently than older threats, right? Like, is it really a great idea to recommend a 5-year-old ransomware sample? Probably not. And also comparisons to mandiant intelligence. And this is done in 2 ways. One, comparisons to that heuristic algorithm I showed earlier for threat actors and malware families, and also to frontline intelligence that's, Mandiant has analysts that go out and work with customer environments, and they generate essentially threat profiles like the model does, but manually. And so if we can do a good job recreating those, the model is performing well. And then finally, and maybe most importantly, is qualitative review, right? So just sending sample recommendations to our subject matter experts, having them assess those and give us some feedback. So here's some numbers. What are we looking at here? This is 2 different versions of the same model, V2 and V3. All these numbers were taken on data collected from the 3rd quarter of this year. The only difference between these 2 models, it's the same architecture, is that one was trained on data from 6 months prior, so V1, V2, and V3 was trained on data from V3. You can see that, like, and I hope this kind of gets to the question of concept drift over time, right? Like, threat landscape's changing, and so as we retrain models over time, we can see that we'll get better performance, right? So we get higher entropy, lower average age, better precision to that subject matter expert algorithm, and also better frontline intelligence precision. One thing that might catch your eye on this slide is these numbers. They look very low, 40% precision compared to like the analyst curated threat profiles, but there's an important caveat here. When the analysts engage with our customers, they run like attack surface tools, so they can see indicators of compromise that actually have been observed in these users' environments or our customers' environments. And so then they map those IOCs to threat actors and malware families, et cetera. So there's a lot of additional context that's there that we don't have access to. But we're pretty happy with that number, 40%, given that we don't have the attack surface data in this version of the model. Okay. This is a lot of text, I'm sorry, but I think it kind of shows the power of the model. So, right, so here we're inputting into the system, hey, show me reports that target the Ukraine and target the aerospace and defense sector. There's 100,000 reports that we can recommend from, right? The model is pulling out the top 10, and if you read through some of these, like the first 2 look really good. There's some lower down in the list that are also very good. And we'll send these to our threat analysts and have them just kind of assess the results. So this analyst basically said that, hey, like, pretty much all of these are matching the criteria given. There might have been a couple of them that were too broad and we'd prefer a different report, but overall, like, hey, good job, 8.5 out of 10, which is pretty good considering like I said, the space for this is orders of magnitude larger than the 10 that we're recommending. Okay, well, what does this look like for our customers? So say we pass into the model targets USA, targets governments, and is espionage motivated. We have different landing pages for the different object types. This is threat actors. We can use the model to measure relevance to the inputs. That's on the y-axis here. On the x-axis, we have how recently these threats were observed, and we can plot these pictures to show like, hey, UNC 2286 is the most relevant to these inputs, but it wasn't the most recently active. We've seen Temp Armageddon more recently active. Might not be as relevant, but something you should consider. So this allows our users to kind of reason and determine what they should worry about. We can do similar things with campaigns, right? So we don't have the pretty plot on this one, but generating campaign recommendations alongside some brief explanation as to why we're showing it to the user. So in conclusion, I showed you guys how you can do some personalized threat intelligence based on heterogeneous object embeddings. results in better org-specific outcomes than, a one-size-fits-all approach. It's very flexible and extensible. And I think there's kind of two key takeaways from my talk that, if you don't remember anything else, I want you to remember this. We're in like an era of increased threat visibility right now in the cybersecurity community. And on top of that, we have a shortage of cybersecurity professionals, right? So I think like our community needs to be focused on data-driven solutions to alleviate these issues. And then this project has really hammered home this idea for me is like off-the-shelf ML approaches aren't really sufficient, right? We tried a bunch of different approaches for this problem. None of it really worked until we like really sat down alongside like the subject matter experts to develop, kind of some bespoke techniques to reflect their knowledge. Here's my references and I'll take questions.
Nice job, Chris.
Hey there. Great work. I was just curious if you experimented with other negative mining techniques to sort of further train the model.
Yeah, good question. Yeah, so we did, like trying to mine like harder triplets, essentially. Yeah, so what we actually found, I kind of glossed over this in like the batch sampling slides, right? Let me just, sorry, it takes a million clicks to get back to these, but, right. We're not just like randomly sampling these things and like randomly sampling the object types after we sample an anchor node. These are like very targeted sampling strategies that were developed alongside the SMEs. So we're like, okay, like sample an anchor actor and then sample malware families in certain ways. I found that like if we tried the triplet mining approach, like harder mining, it kind of had a negative impact for our setting. I think we tried to kind of do a more bespoke solution to where like the mining isn't really giving us any extra lift. Thanks for the question.
Great, Turks. I have one question. In regarding to the input condensation, like how do you address like different input representation from different intel? Like did you face like some entities are not rich enough like when you pass to your model while others are? And my second question maybe it's kind of related to that. What's the average days in your experiment like for the worst model?
Okay, thank you for the questions. So you're talking about, feature observations for like given nodes. Obviously there's some, like for example, threat actors, we have a lot more intel on than others, right? So we have a much better representation for those. And I think your question was more so related to object features, but if you think about it in terms of like the graph setting, you can imagine that there's some threat actors, like everyone knows about APC 43. There's a ton of data on them, ton of relationships present, a ton of intel, ton of previously observed attacks. There's other threats with, that's much more sparse in the space. So essentially what we've had to do is like, we do have some guardrails on top of the model, right? So the model will generate recommendations. And then there are certain like, combinations where, hey, we don't have a ton of data for certain countries, right? So, do some post hoc filtering to ensure we're not, just recommending things because there is a lot of uncertainty in certain areas of space. Your second question?
My second question is in regard to the experimental result. You mentioned that average days around 30 days are for the model, and what would be for the worst model you got like?
I think it started off around like 6 months or something like that. The Mandiant Intel data set goes back 20 plus years. So if you're getting under 30, like a month, it's pretty good considering we have 20 years of data.
All right, time for one more.
This is amazing. I have so many questions, but I'll just ask one that I had in mind is when you were doing the testing, you talked about a bunch of different features or factors like target locations and threat actor relevancy that people can add in. Did you find that certain factors like carry more weight than others in the like accuracy of the ultimate recommendations or?
Yeah, no, that's a really, really good question. And maybe an unsatisfying answer, I guess I'd say it depends. All right, like the way like I've learned a lot from talking to the threat analysts, and the way they reason about problems is very different. They take a lot of external context, like geopolitical information, or like knowing like certain actors are more financially motivated. We did find that like adding in like the ability for users to like ask for actor motivations was quite important, right? Like kind of without knowing that you care more about like a ransomware threat actor versus versus like an espionage threat actor was rather important. And that context isn't really necessarily available without those inputs. So yeah, it kind of depends on the particular input combinations you're looking at, but thanks for the question.